welcome back. Respected Dr. Surya Prakash sir. Welcome sir.
Yes ma'am, good morning. Thank you.
The topic for this session is optimization of biometric recognition system. Now I request Dr. K. Anupriya madam to introduce the resource person.
Thank you, Sharwani. It gives me great pleasure to introduce today's resource person, Dr. Surya Prakash. Sir received doctorate from IIT Kanpur in the year of 2013. Currently, sir is working as an associate professor in the Department of CSE, IIT Indore. His research interests are biometrics, machine learning, deep learning, pattern recognition, computer vision, image processing, big data, digital heritage preservation. Dr. Surya Prakash published more than 33 journal articles in well-reputed papers. Sir is guiding 2 research scholars and 3 were awarded. Sir got 4 research-funded projects from various funding agencies. And he also organized various workshops, STTPs, conferences and webinars. We are honored by... Thank you, sir. And now I request Dr. Surya Prakash sir to take over the session. Over to you, sir.
Yeah, thank you, madam. I hope I'm audible properly. Hello. Hello.
Yes, sir.
Ma'am, I'm just asking if I'm audible properly.
Sir, hello.
Am I audible?
Yes, sir. Now you are audible, sir.
Okay, good. In case if I'm not audible, please let me know. Please.
Okay, sir. Okay, sir. Thank you, sir.
Yeah. Is my screen visible now? Madam, is my screen visible?
Yes, sir. Visible, sir. Visible, sir.
Okay. Thank you. So, good morning, participants. In today's this talk, we will see how to enhance the images, contrast of images, using a swarm optimization technique, which is called artificial bee colony. So, whenever we are dealing with the biometric images, we have images of various kinds. Very good quality images, some might be of very bad quality. So there are some factors which actually affect the quality of the images. We will see some of them here. But one of the factors that actually affect the quality of the image is the contrast. Right? So whenever you have, let's say you're doing face recognition or you're doing ear recognition or any like even in iris, the image that you are using, if whether it has a good contrast or bad contrast, actually determines its quality with respect to this particular parameter, and any image which has good contrast is always desired. So here, with the help of this algorithm, we'll see given an image which has poor contrast, how to enhance the quality of that image. That means how to enhance the contrast of that image. So that is what we are going to discuss in this in detail in this presentation. And this presentation is basically based on one of the paper that was published in 2015, where we have proposed an algorithm which is based on ABC to enhance the contrast of an image. And this work is actually mainly done by my one of my students, Piyush. Right, so let us go into. In case if you if you feel that you should use this technique or you need more details about the technique, so this link is there. At the end of the session, I will be sharing the presentation with you, so you can download this paper and then go through it to get more details, because we have limited time here, so we may not be covering all the aspects of this here. But if you need more details, I request you to please go and download this paper and then just see that. Okay. So this is the way we have to go with this talk. So first we'll see some basics, the introduction part of this talk, and then we'll see the role of ABC in enhancing the contrast, or how ABC can be used for enhancing the contrast. And please remember, this ABC is nothing but this. I might be referring to this abbreviation, but note down there this is artificial bee colony. That's a short form for the artificial bee colony, and this is a bio-inspired technique, or you can say this is a swarm intelligence based optimization technique. Okay, so we'll see briefly ABC, and then we'll see there is some results, and then what are different applications where this can be used. Okay, so in the basics, we are first going to discuss what are the factors actually which are responsible for determining the quality of the image. Right, one of the factors is the contrast. Contrast in a little more detail, and then we'll see that we know that histogram is a histogram is a good representation for any image, and there are some techniques which use histogram like for enhancing the contrast of the image. So we'll see that very briefly, and then whenever we are using any optimization technique or any swarm intelligence based optimization technique, always we have a objective function or the fitness function, which is like the main part of the algorithm. So we will be seeing how we are defining the objective function here. These all covers the basic, and once we are done with this, then we'll go for the ABC and then the results that we have obtained from this algorithm. So here I have listed some of the factors actually which are responsible for the poor quality images, right? And I have taken the example of the face recognition, where you see the face images here, but this is true in general. And wherever you are using images, if the images have bad contrast, then the quality of the results will not be good. These are some factors, not bad contrast, it's bad quality basically, or poor quality. So these are some factors which are responsible for the poor quality, like if your image has a very high contrast, then also it is it will give a bad quality, it will be considered bad quality image. If the contrast is very low, then also in that case we say that the quality is not good. A little later we'll see what exactly we mean by contrast. And then if the image is not properly illuminated, or very blurry, every part of the image should be properly illuminated. Here you see in this part of the image, this is not properly illuminated. Are there any questions? I request all the participants to mute their mic. Okay, so bad illumination is also one factor which makes the image quality poor. Noise is another one. Like if your image has noise, then obviously the quality will be poor. Sometimes the image has blur, and this also actually contribute to bad quality images. So these are some of the factors. There are a few more. I've not listed them here, but these are the factors which are primarily responsible for bad quality images. So here we are going to focus on mainly enhancing the contrast of images. You can say overall objective is to enhance the quality of the image, but we are enhancing the quality of the image with respect to the contrast. Right? So we are trying to improve the contrast. So this whole discussion is going to be based on contrast. So in very short, we can say that the contrast is actually the difference in color or the intensity that makes an object distinguishable. Okay? So normally in the image you will have some, you can say some objects are there and some background is there. So whenever there is a good difference between the foreground and the background, then whatever the object being displayed in the image, that will be properly visible. If this difference is not proper, then if it is like the difference is too high, that means some of the areas are very bright, some of the areas are very dark, or if it is very low, that means all the areas in the image, they are almost having a similar intensity, then in that case we will say that the contrast is poor. So this basically contrasts, as you say, this is the difference in the intensity or the color that makes object distinguishable. So we want a proper value of this. We don't want very high contrast, and also we don't want very low contrast. So this is very important to remember. Proper contrast is required so that things are visible, but they are not either too bright or they are not too too dull. Okay, so here you see one example where you have increasing contrast. You have one image here, and this is artificially created example, so that you know like what is the meaning of increasing contrast or high contrast. So you see here when you are moving from left to right in this sequence, the contrast is increasing. So here you see this image has a very good contrast. The first image has very good contrast, but as you are moving from left to right, some parts are becoming very bright and some parts are becoming very dull, right, or very dark. So at the end, you see this image has very poor contrast because some places are really very high and some places are really very dark. This is another example where you have again we are almost starting with the same image, but here the contrast is decreasing. So here you have, like, if you see this picture, you have good good differentiation between the different parts of the object, parts of the image. But as you are moving from left to right, the contrast is decreasing. Right? So here you have little poor contrast, still further poor, and then at the end you see that this contrast is really very poor, and you are not able to differentiate what exactly this image is representing. So we are making use of this technique, which is based on ABC, improve the quality of the image. Okay. Here is an example. A good, you can say, good tool or good mechanism to analyze whether the contrast of an image is where you have very low contrast. Another image here on the extreme right, which has very high contrast, and this is one image where you have, you can say, the acceptable contrast. Okay, so if you analyze their histograms, I hope you understand what is the meaning of a histogram of an image. If you don't know, if this is basically in the histogram, on the x-axis we have the different gray labels that we have in the image, and y-axis tells us the number of pixels present there. Right? So for example, if this is a gray level 50, and if you have a, let's say, a line 225 or so. So on the x-axis you have gray level, and we are talking about most grayscale images, which are the 8-bit images. So the grayscale will vary from 0 to 255. So that is why you see on the x-axis you have 0 here, and then 250 is written, but little more further you can get at the end it is 255. So on the x-axis you have these gray labels, and how many pixels in your image have that gray label, that is plotted on the y-axis. And if you get this kind of plot, then basically this gives us the histogram of an image. So now here we have three plots, three images, and corresponding to them three histograms. Now you can see the characteristics of the histograms when we in the dull image you see you see that all the pixels are having the intensity between 100 and 100 and 150, right? You don't have other number of any.
Sorry to interrupt you, sir. Your voice is breaking in the middle, sir.
Okay, ma'am. So, is it really? I mean, breaking too much?
No, sir.
No,
Okay,
if it is.
sir, now it's fine, sir.
Okay, no, then actually I can change the internet connection and then try.
Yeah, sir.
If it is really, so shall I try changing the internet connection?
Sir, if possible, please, sir.
Okay, let me just change that. Just a minute. Am I audible, ma'am?
Yes, sir. Audible, sir.
And is it better?
Yes, sir.
Okay. So fine. In case, I mean, again, yeah, again, if there is a problem, please tell me. Again, I will switch to the previous
Okay, sir.
one. I don't know like which one will work better right now. So
Okay, sir.
yeah, so really sorry if I mean it is getting problem. Yeah, and actually I have closed my video also, so maybe because of the bandwidth, I mean the video when it's taking the bandwidth, it might be getting little problem. So I closed my video, and I request participants if they have any questions, they can actually stop me at any point and then ask the question. All right. So I was actually just discussing here that we have three different types of images. One very poor, I mean, two images which have very poor contrast. In one case, we have very low contrast. In another case, we have very high contrast. And then at the center, you have a good image which has acceptable contrast. And can you please mute all the participants? Okay, so here you have, so you see, so in case of low contrast, all the pixels will be accumulated at one place. In the case of high contrast, you will see a lot of pixels being getting accumulated at the two extremes, like on the left end, that way, which is representing a very low intensity, and the other end, on the extreme right, which is representing the highest intensity. So in case of very high contrast, you will see the good amount of accumulation of the pixels at these two extremes. And in case of good contrast, you will see that these pixels are distributed across all the intensity. So here you see, in this particular case, the pixels are, you have some number of pixels which have intensity 0, 1, 2, 3, up to 255. You don't have any intensity where you don't have any pixels. So it is like almost distributed across the grayscale range. And theoretically, for a good contrast image, we should have this histogram uniformly distributed. There is a technique called histogram equalization, which basically does this. Given any histogram, it takes and then equalizes it or distributes it so that it becomes uniform, and that's where it increases the contrast. So please just remember, I'm highlighting this here to tell you that with the help of contrast, you can actually with the histogram of an image, you can actually get the idea about the contrast, whether it's a good contrast or the bad contrast. I mean, the image has good contrast or it has bad contrast. So ultimately, the objective, whenever we are let's say improving the contrast of the image, our objective is normally to distribute the pixels across all the ranges. So let's say this was the, this is one example of a histogram where you have this kind of pixel distribution. Now, when you change the histogram in such a way that it gets distributed uniformly, then corresponding to that, whatever image you have, that will give you the better contrast. Okay. So, as I just stated at the beginning, that we are going to use histogram equalization here for for the contrast enhancement. We are going to use ABC algorithm. So we're now going to discuss that. And before that, as I stated at the beginning as well, that for any optimization technique, you need a objective function, right? Or based on that fitness function. So we will first see how we are going to get the objective function in this particular case, and then based on that, we'll see how the ABC is formulated and it is applied for this problem. And this objective function here is based on the quality. So normally, whenever we have an optimization problem, we have an objective function, and we want to, we want to optimize that function, right? In the problem, our objective is to get, let's say, some set of values, the values for the variables, so that you have the optimum value for the objective function. So here our objective function is the image quality. So when we are using ABC to do the optimization, basically our objective is to improve the quality of the image. So what we will be doing here, every time, let's say you have a, let's say, solution. So based on the solution, we'll see what is the image we are getting out of that, and we'll check the quality of that. If the quality is improving, we can say that yes, with the help of this particular technique, we are improving the contrast. Right? So quality will be the measure of finding out whether the solution that we are getting from this optimization algorithm is actually a good solution or it is a bad solution. So wherever, let's say, and too much disturbance is coming. Can you please mute all the participants? Yeah. In the when we are applying artificial bee colony for improving the contrast, every time we get a solution or a new solution, we'll see that a new solution. Then we'll see the image. We'll check the image quality. If it is improving, then we'll say that yes, the solution is a better solution. Otherwise, we'll say the solution is not a good solution. Right? So this whole objective function is actually based on the quality value. So given an image, which we will be generating based on the solution, and given that image, we'll check the quality, and if the quality is improving, then we'll say that we are going towards achieving the optimum for the objective function. Okay. So now let us first discuss how the quality is being assessed here, and then based on that, we'll discuss the ABC. So as I stated, so objective function for this ABC algorithm that we are going to use here to optimize or to improve the contrast, it is going to be based on the quality estimation. And when we are applying this algorithm, as I stated, quality of the solutions we will be checking. That means the quality of the images we will be checking, and wherever we have the improved quality, it will tell us actually that the solution is a better solution. Okay, so overall objective is basically to estimate the quality and try to improve that. Okay, and so here quality estimation actually, which is a kind of objective function here, as I said, it is actually motivated by the functioning of the retina. So the algorithm that we are going to see here, that is actually going to compute the contrast of the image, or maybe based on the contrast, it is going to compute the quality of the image. And in process of computing the quality, or in a way we can say, because the quality is, we'll see quality is based on the contrast. So to compute the contrast, we will be using actually the phenomenon that we see when we are projecting some object on the retina, or when we see, we are going to use the concept which we say that is actually applicable when any image is formed on the retina. Okay. So retina is actually there are two important things which are actually there with respect to retina. I have given the reference for these two properties. If you have any interest, you can actually go to these links and to these papers, and you can get you can explore more. But here, so this, I'm just listing the two important properties. So it is in the retina, we see the perception that we get in retina. It is based on the centers around retinal receptive field and the presence of multiple spatial frequencies. Right? So based on these two factors, considering these two factors, I'm not elaborating more on this, but considering these two factors, we have a technique called local band limited contrast computation technique. What this technique does, it actually uses the concept that is being followed in case of retina, and then based on that concept, actually it computes the contrast of the image. Right? So here it is just important to note down that for calculating the contrast of the image, we are using this technique, and this technique fundamentally actually relies on the way perception is. We get the images formed in retina. Okay? So essentially, to compute the quality of the image, we are going to first compute the contrast of the image, and based on that contrast, we are going to compute the quality. And how we are going to compute the contrast, that is actually with the help of this technique, local band limited contrast technique. So let us see first this technique. So as I just stated, this says that the quality estimation here makes use of the local band limited contrast, which is defined as follows for a pixel xy. Right? So your image is collection of several pixels, and in this technique to compute the contrast of any image, you have to basically compute the contrast of all the pixels, and then collectively you have to tell what is the overall contrast. Right. So at xy pixel xy, this is the formula actually used to compute the contrast at a particular pixel. It says that the contrast at xy is equal to lambda xy divided by beta xy. Now what is lambda xy and what is the beta xy? They are defined here. So lambda xy is like a filtered image, which has and this filtering has been performed with the help of a band pass filter. And beta xy is another image which is a low pass filtered image. Right? So to generate you can say to generate contrast for an image at different places, you first create lambda xy or lambda or beta. Given an image, you create lambda and beta. Lambda is created by filtering the image by using band pass filter, and beta is created by filtering the image using a low pass filter. And once you get these images, then again from those images you can use the xy values for the lambda and beta, and you can substitute those values here, and with the help of those values you can create the contrast for the given pixel. Okay, so this is the way the contrast for a pixel is calculated using local band limited contrast. And this band pass filter that we are using here, this can be actually created with the help of difference of Gaussians. Right? The band pass filter, particularly in this case, the first filter that we are using here, this one, it can be actually created with the help of DOG, which is the difference of Gaussian. So here we are defining this O as O is equal to C minus S, where you have C and S, these two images created by convolving the original image or original function f by two Gaussian functions. Right? I hope you have some background. You know how the difference of Gaussian is created. So basically, in very short, I can say that when we are creating the DOG image, this is basically the subtraction of the two images, which are you can say filtered using a Gaussian with two different sigma. Right? So here you have same image being filtered by a Gaussian which has, let's say, sigma 1 value, and same image is filtered by another Gaussian which has sigma 2 value. Okay, so with the help of two Gaussian, you are, let's say, you can say that you are smoothing the images, and then you are subtracting these two images to get this OXY. So OXY is a OXY becomes a band filter image. Okay? So here the question comes when you are saying in the previous slide when I said that this is a band pass filtering. So how you create that band pass filter? So that band pass filter is being created using the difference of Gaussians. And once you have this band pass filtered image, then actually you can modify or rewrite this formula. So this in place of lambda, you can write this O value. And what is your beta here? Beta is actually a low pass filtered image. So low pass filtered means you can actually substitute this image, the denominator, by the S here, because S is how you have created S. You can see that S is being created here by convolving the original image by Gaussian. Right? So this is whenever you are convolving any image with the Gaussian, it becomes a low filtered. That convolution with the Gaussian is a low pass filtering operation. So this SXY, this image or this function is basically the low pass filtered value that you can actually keep in the denominator. So that way we get a modified formula here for computing the contrast at a particular place. Right? If you have not understood anything, you can just actually remember this formula, or and later you can explore more about it. This formula basically says that you have a given image. For that given image, you get this DOG image, and you get a smoothened version of that image, and then you keep you divide these images pixel by pixel, and then you'll see you will get the contrast for different pixels. Okay. One more thing we actually see that when we have multiple, when we are do visualization using the retina, in retina actually this visualization happens with the help of different frequencies, multiple frequencies. So that notion is also actually being incorporated here. So when this contrast is being calculated, this contrast is actually calculated for some n number of frequencies, right? So for that n, the value of that n is actually 10 here. So for the 10 different frequencies, we have the 10 different frequency values, and for all those frequency values, basically sigma 1 is computed, and based on that sigma 1, we compute the sigma 2. So when you are creating those DOG images, those DOG images are computed actually for a set of sigma 1 and sigma 2 values, and these sigma 1 and sigma 2 values, these are basically created with the help of these different frequencies that we are considering. And here we are considering, in general, you can say you can have n frequencies, but here the value of that n is 10. Okay, so now let us see how the quality is computed based on this the contrast value. So you know that given an image, you can actually compute the contrast for different pixels. So here this computation is done blockwise. So the whole image is divided into blocks, and then for every block we are computing the overall contrast value. So for each block I mean, we are talking about the ith block in the image I, the contrast CXY is computed like this for its all pixels. And once you have this contrast value, then overall contrast value CBI for that ith block is actually computed by summing the CXY for all the blocks. Right? So you have a patch of size, let's say 10 cross 10. So you have 100 pixels. For all 100 pixels, we have computed the CXY, and then you have summed that up to get the overall contrast of that image. Okay. Now we know that too much contrast is also bad. Too low contrast is also bad. So when we are computing the CBI value for any patch, we don't want this value to be very high, or we don't want this value to be very low. So whatever the contrast we have obtained for this particular patch, whether it's a good contrast or bad contrast, depending upon the, actually we are assigning for every block, we are assigning a binary value 0 and 1, where basically 0 is saying that the contrast is good and 1 is saying that contrast is not good. Now when contrast will be good, so there are two thresholds which are experimentally decided, and if your this CBI, the value of the contrast of a particular block, lies between T1 and T2, then we say that it's a good contrast, and we assign binary value 0 to it. And then if it is not in that range, if it is like it is less than T1 or it is more than T2, which basically mean that it is either too high or too low, then we are assigning one value to it, right? So based on this binary value, we can actually calculate now overall quality of the image. Now I hope you have followed up till this point, and you can say that based on this value, we can tell whether a block is good or not. And let's say you have created 100 blocks or 100 patches in your image. So then out of those 100 patches, how many patches are good patches, how many patches are bad patches? Based on that, you can calculate the quality of the image. So this is the overall contrast being calculated for the given image I. So here you have let us say Bij or Bji, it is actually telling about a particular block. So you have, let's say, total NB number of blocks, right? NB patches you create. And as I said, this is done for 10 different frequencies. So this total J from I equal to 1 to 10, it tells you how many different frequencies you are going to consider, and for every frequency you are going to consider NB blocks. So overall, basically you are creating these many blocks, and for all those blocks collectively, if you consider the contrast, then this QC value gives you the contrast of all the blocks. Okay. Given this QC and QC, please remember this value is since we are using this BJI here, which is a binary value in the previous slide we have seen. So this QC is QC is obtained by summing the 0 and 1 values that you are getting corresponding to these blocks, right? So what is the highest value you can get when you have I mean, what is the highest value we can get for this QC? So we know that we have how many total blocks we have? We have 10 into NB blocks. Outer loop ranges from j equal to 1 to 10, and this inner loop ranges from j equal to I equal to 1 to NB. So we have total number of blocks as 10 into NB. Okay. And QC will be actually counting how many, I mean, you know from this here, we are summing 0 and 1. So QC will tell how many blocks have value 1. Right? Because if QC is 20, this means that the 20 blocks have value 1, or other way you can say that 20 blocks are bad, because one value you see here, one value is assigned to the bad blocks. So collectively, by considering the value of the QC, you can actually find out the quality. So let us examine the two extreme cases. One where QC is equal to the denominator, right? That means all the blocks in your images that you considered, all the blocks are 1. Right? That means all the blocks are poor. All the blocks have poor contrast. So in that case, QC and denominator, they will be same. So this value will be 1 total, and 1 minus 1 will be 0. So that means the quality will be bad. So if you have a big image where all the patches are poor patches, right? So if all the patches are poor patches, then this QC will be equal to the number of blocks, and then this value will become 1 and quantity will be 0. In the other extreme, when let's say all these blocks are given 0 value, so then the second factor will be 0, so the quality will be 1. So this equation tells us the quality of the image based on the contrast value. Here in this example, we demonstrate that the quality index varies this way. So when contrast is increasing, when the contrast is low, you have a poor quality. When contrast is very high, you have poor quality. And when you have contrast at the middle, we are calling that 0, which basically mean the ideal contrast. So in that case, you have the highest quality. So in the plot, we see that as the contrast is increasing or decreasing, the quality is increasing. And at the middle, you have some a place where you have a better quality image. So this low value of QC shows that very high or very low contrast is there, and whatever the QC we are getting, which indirectly tells about the quality or the contrast of the image, we formulate our objective function or the fitness function, and then use it in the ABC algorithm. Okay. So now let us see the computation of the optimal cell. Yes.
Sir, any in the last slide, any range of the contrast, sir, minimum to maximum?
The value?
Like
yes,
sir, the value. Like 120 minus 127 to 127 here in this slide. Sir, this is the fixed range, or this can be varied?
No, theoretically, it can lie in any range, because see, I mean, we have actually normalized it in such a way that this falls between minus 127 to 27, and the ideal or the ideal contrast actually comes at 0. But
actually, sir, the gray level range is 0 to 255. So I think
no, that is
I can.
No, that is why I'm saying that. So we have actually normalized. So whatever the value you get in an image, you can normalize them again, right? Like we have different types of normalization, like min-max normalization. So what you are saying is correct. So now, normally when we are dealing with the images, we have all the positive values. Intensity will range only from 0 to 255. But here, we have actually rescaled the value in such a way that the ideal actually comes at 0, just to show that. And poor is on one side of the negative, and then I mean, like the low contrast and the high contrast is on the other side. Is that okay? I mean,
okay.
So what you are saying is correct, but we have actually rescaled the value so that the range looks like this, so that the ideal is at the middle 0. Okay.
Okay, sir.
Yeah. So let us see now how the optimization is being performed with the help of artificial bee colony here. And one more thing, I think since you have asked this question, so whatever you are getting here, whatever the values you are getting for the contrast and whatever the values of the CXY you are getting, they need to be actually normalized to a particular range so that proper thresholding can be done, proper thresholds can be defined. Right? So if let's say your values all lie between 0 and 100, let's say, so then putting a threshold will be very difficult because one time it is lying between 0 and 100, another time it might be lying between 0 and 200. So whatever values you are getting for the contrast, they need to be actually rescaled to a particular range so that the threshold that you have decided is applicable for every image. Right? For example, I mean, if you see this expression, it says that when the CB value is between T1 and T2, then you have to consider it's a good contrast, right? So now a particular, let's say this T2 is 100. So you're saying when the value is less than 100, it's a good one. But in one of the images, maybe you have only values, highest value as 99 or maybe 75. Then how will you threshold this? So again, we need to actually rescale the value so that every time whatever threshold we have chosen, that is applicable to the image, because we can't decide this threshold for every image separately. So that is why this rescaling is required, and we have chosen to rescale the values in this fashion. So let us see now the optimization, and here we are going to see the artificial bee colony, and this is actually based on the natural honeybee colonies. So let us first see very briefly what we have in the natural honeybee bees colony, and then based on that we'll formulate the ABC. So in case of natural honeybees, and basically what honey bee does, I mean, we know that it goes to different flowers, pick something from that, and then create the I mean, accumulates it at one place and bears the honey. So objective is to accumulate more and more honey. So when you are collecting these things from different places, you need actually those places are called the food source. So we need actually a good food source so that you can actually ultimately get the good accumulation of the honey. So here we can say that I mean, in our true case, when you are going to use it for increasing the contrast, we can say that we want good solution so that our objective function gets optimized, right? So their objective function is like accumulating the honey. So here we have, it seems they have 3 types of bees which are doing this task. So I mean, naturally we see that all the bees are looking same, but when it is analyzed closely, we see that these bees are doing 3 different types of tasks, or based on that we can say that there are 3 types of bees: the employed bees, onlooker bees, and then the scout bees. So based on that you have the formulation here as well. So what employed bee actually does, so it searches the food source with the help of its memory. So it has some memory, and based on that it goes to a particular place and then accumulates the things from there, the honey from there, you can say. So we will see that I mean, normally we will start with the random values in our case, but as we proceed based on some of our information, this can be further improved. So employed bees, you can say that they create actually in some way the new solutions, right? Because they, based on the memory or the past information or whatever the information they have, they create they create the food sources, or they searches for the new food sources. And what is the role of the onlooker bees? So they actually first find the good source from the employed bees search, and then searches around that particular source for a better solution, right? So in some sense you can say here you are doing kind of initialization, you are creating some food sources, but out of those food sources which one is good and or bad, that is actually explored by the onlooker bees, and then wherever you have the good source, they are actually being promoted and then they are used. Sometimes in case of scout bees, actually searches for the new food source randomly. So sometimes we see that whatever the food source you have here, which you have obtained from the employed bees and which is being improved by the onlooker bees, you find that it is not improving, right? So in that case, you need to abandon that solution, and then you need to or abandon that food source, and then you need to search for a completely new food source. So that is actually being done by the scout piece. So, so the same notion we are going to use here for implementing the bee colony phenomenon, and we are implementing it for the artificial case. You can say there was the natural phenomenon, and we are replicating that here. So it becomes the artificial bee colony. Okay. It was actually proposed around 2007 by Karboga and Berserk. The paper where this ABC was proposed is written here at the bottom. Again, to explore this more, you can go to this paper and then get more details. Here I will be mentioning very briefly about the bee colony. So bee colony is it is motivated by the natural honeybees, and it is being used for several optimization problems. Right? We are going to use it for the contrast enhancement, but it has been across the ranges, across the disciplines of engineering and sciences. It has been actually used for for performing the optimization. Right? Here we are going to use in ABC. We are going to have the notion of employed bees and onlooker bees and the scout bees. So we are saying that we are doing employed wherever we are implementing the notion of the employed bee. We are doing what onlooker bees do. So then the last this called the look. Okay. Here. So whenever you are, like say, improving the solution or creating the new solution, we need some indication. I mean, one way is that you perform it randomly, but if you have, let's say, some information known, then you can take some informed decisions. So here we are actually making use of the histogram, and based on the histogram, we'll see that we are defining some direction constraints, and with the help of these direction constraints, we actually we are able to put the algorithm in right track so that it moves in the right direction. So first we'll see the use of we'll define the direction constraints, and these direction constraints actually we are using when we are generating the solutions. So let's first see what are the direction constraints we use here. So you have as I already explained, so then we know that whenever you have a good contrast image or the bad contrast, when you have a good contrast image, your histogram is uniformly distributed across the gray levels. But when you have a poor contrast image, either the histogram will be accumulated at one place, or that means all the intensities, all the pixels will have the similar intensity, or you will have the accumulation at the extremes, right, extreme ends. So in both the cases, this is a poor contrast, and that will be actually giving us the bad quality image. So if you can find out actually that what kind of contrast the image has, or what kind of histogram the image has, based on that actually we can initialize the solutions properly. So here the solution vector that we are basically using here for the optimization is an n-dimensional vector. And how we are initializing this n-dimensional vector? So this is basically representing the pixels. So pixel intensities are between 0 and 255. So by using this range, the solution vector is basically being assigned, being initialized. This is the general formula for computing the or for, let's say, performing the initialization in case of artificial bee colony. Right? If you go to that paper, you'll find that this formula is there, and this is true for a generalized case in general. Right? I mean, whenever you are doing the optimization, you have some constraints that the values should not go beyond this. So with the help of those constraints, we perform this initialization. So here in this formula, you can treat this formula as a generic formula. Here you have a lower bound and you have an upper bound. So L and U, they are defining the lower bound and upper bound. In our case, lower bound and upper bound could be 0 and 255 because we are talking about the intensities. Let's say you have you have an optimization problem where you are, let's say, you have two variables x1 and x2, and you are optimizing this function x1 square plus x2 square, right? And let us say you have put a range on the x1 and x2. You are saying that x1 and x2 cannot be more than -5. They cannot go beyond -5 and let's say +5. Right? So this is a constant. So what is the L1 here and what is the L2 here? We know L1 is -5 and sorry, L1 is -5 and not L1, I should say L only. So L is -5 and U is +5 in this case. So lower bound is -5, upper bound is +5. So similarly, in case of images, this lower bound and upper bound is 0 and 255. So this is the generic formula for initializing the solutions. Now we'll see that with the help of those direction constants that I was talking about in the previous slide, we can actually improve this this initialization. So here we see that, let us say you have a image where you have high contrast, very high contrast. That means accumulation is on the extreme ends. You have some points pixels accumulated here and some points accumulated here. And remember that for a good contrast image, this need to be equally uniformly distributed. So we can say that these pixels, more pixels that are accumulated here, they need to be brought to this range. Right? So whatever intensity your pixels have, they need to be hello.
Yes, sir.
Okay. Interruption in the connection, so I thought I was not sure if I was audible or not. So okay, fine. So let us continue. Yeah. So yeah. So for the high contrast images, our objective is to actually initialize, initialize the values or give the intensities to the solution in a particular range. Let's say, so here we are saying that our L1 and L2, L1, so L and U, they are not ranging from 0 to 255, or they are not the value, they are not holding the value 0 and 255 respectively. They are restricted to hold the value between R1 and R2 only. And why we are saying this? Because already we know that a lot of pixels are accumulated here and here. So we want them to go back here. So when we are doing the initialization, we say that the initial intensity that we want to give, that we want that it should, some kind of all these probably some based on some random numbers. So we are doing this, but we are saying that this is not always done. In most of the cases, it is done. So you are generating a number between, let's say, 0 and 1. Whenever that random number is more than 0.3, then we are doing this. And then if it is not more than 0.3, then we will be doing only this, because we don't want all the pixels to go and accumulate at the center also. We want some pixels to get accumulated or to be present at the end as well. So, and you know that when you are generating a number, a random number between 0 and 1, you are saying that when number is more than 0.3, then you are doing this. So the range is more for this. You are generating a random number, it is more probable by this condition. So for all those cases, the initialization will be done for between these two intensities. And in some cases where the random number is falling less than 3 or less than the lower and upper boundary at 0 into 55. Okay? So this is we are doing with in case of high contrast. In case of low contrast, what happens? In the low contrast, we have all the pixels being accumulated at center. So we want this to be distributed across the range. So here we are considering L and U as 0 into 55. So depending upon what kind of image we have, actually we can have an informed initialization, and to get that informed initialization, these direction constraints are actually helping. Once we have initialized the values, then the role of the employed B comes, and all these employed B's that we have, they actually try to improve the solution. Please remember, in all these optimization, I mean, particularly, I guess, let us talk about the artificial bee colony. So when we are doing the optimization, it is not the process done by several bees. So here also we are selecting the starting points from where we are actually parallelly, you can say, we are parallelly going and then exploring for the best solution. So that is why you see actually you have two indices here. We are saying Vij. Vi actually ith index is telling you the ith solution, and in I have n values as I said. So j basically dealing with that that value, right? So you can say one solution of n, which is n-dimensional vector, another solution is n-dimensional vector, and several, you have several solutions. So to index, to tell that which solution we are talking about, we have I, and in this direction, in a particular solution, which value we are talking, that is decided by the j. So in all these cases, you have two indices, Vij. Okay? So here, with the help of employed B's, all these initial solutions that we have, they are basically improved, and this is the formula for improving the solution. I'm not going into the detail of this, but what basically is saying that xi, and so to improve that jth value of I, you are considering the existing value of xij, and then randomly actually it is selected this xkj that you see here. So this again, this is the jth value from the kth vector. So this that where you are doing the improvement, let's say this is I, and another vector, let's say it is here, this is k. So by considering the jth value from these two vectors, from this first vector and from the kth vector here, sorry, from the ith vector, we are computing the new solution. Okay? And in this process, you see that there is a constant here phi, which is basically it's a random number which is generated between +1. So based on the given values xij and xkj, and randomly chosen this value phi, this new value for the xij is being generated. This is done for the all employed bees. If we have employed, let's say 100 employed bees, for all of them the solution is being updated. And again, this is a greedy approach here at this particular stage. So if when you have a old solution and when you are computing the new solution, if that new solution is not improving, then we are not considering that. If it is improving, then we are considering that. So based on the strategy, we are actually okay. So here to find out whether a solution is a good or bad, again, we will be using that objective function that we defined earlier. So we'll compute the quality of each newly generated solution, and if it is improving the quality of the image, then we'll say that that solution is a good solution, and that new solution will be treated as the current, will be maintained as the current solution. So after completion of the employed B, each onlooker B probabilistically select solutions roulette wheel process, and it update it following equation. So again, some kind of updation is happening here. This roulette wheel process, you can assume that's kind of randomization process to generate to select the solutions randomly. So once once the onlooker, the symploid bees have actually finished their work, then the role of the onlooker bees will come, and then probabilistically it will select a solution and then update its neighbors using the following equation. We have used, the formula is quite similar, right? As you see here, we were talking about xij and xkj. But here, xij here again is the old solution or the old value coming from your ith solution, and this xcj here is chosen. It is the chosen solution, which is chosen based on the roulette wheel process, or we can say it's a randomization process, and out of Vij is the new updated solution, and in this particular case, here the solution was, when the n employed bees were working, the solution was sometimes improving and sometimes it was not improving. But here, every onlooker bee will actually consider a food source or the improve it. If it is not able to improve the current, let's say, new food source, and then try to improve that. So that way, this process is previous process, and the role of the scout bee. The solution is not improving, so you find that you have iterated through cycles, and the solution is not improving. So in that case, that food source or that particular solution need to be abandoned, and then new solution need to be considered. So that is decided based on the iteration limit that we set. So if particular solution has not improved a fixed number of times, if that value is, let's say, more, and then change the randomly again create a new solution to work on. Okay, so this is the whole process that, and here the main thing, the objective function is being defined with the help of quality. So when solution, basically we are improving the quality of the image, and indirectly we have seen the quality is, so if the quality of the image is improving, this means the contrast is improving. This has been actually tested on the two databases actually we have used for the testing of this the proposed approach. AL extended phase database is a normal database where you have some phase images. You don't have the contrast, poor contrast, or good contrast, bad contrast images. Normal images. We have actually created the good contrast or bad contrast images from the images, and then we have used for our testing. So this database contains around 38 persons, and we have used this tool called Chimp, which is an open source cross-based platform tool, which is available for different platforms like Linux, Windows, and Mac. With the help of this tool, actually we have given an image, we have created different versions of the image, and these versions, some of them are having very high contrast, some of them are having very low contrast. So at the beginning, if you remember, I have showed you contrast with the help of this tool. Okay? Because there is no database where you have contrast, increasing or decreasing contrast images present in any standard format. So just to create a standard setup, we have you can say we have considered some kind of neutral or good contrast images, and from that, by improving or by increasing or decreasing the contrast, we have created low contrast and high contrast images. Okay. Some of the images we have also obtained actually from this because for the comparison purpose, we have taken some images from this particular paper, and then we have broken down that. In the result analysis, we have analyzed the results in two ways. One, by analyzing the visual quality, which which is performed by the human subject. We are applying this. We have having poor contrast, then we are applying this algorithm, and then seeing whether visually we are seeing whether the quality is in. quantitative, quantitative analysis, which is based on features. So we'll see what kind of features we are using. So you see here, left side you see an example where enhancement of the contrast is being done and the quality is being inspected visually. So you see this image has little. This image also has little poor contrast. You see that all the pixels are accumulated at one place. In this, most of the pixels are actually accumulated on the half of the intensity range, right? So because these histograms are not equally distributed across the range of gray levels, they are actually creating a bad contrast image. So when this algorithm is being applied, these are the two samples, and here we see that if you compare the histogram that we are getting here, this histogram has more uniform distribution compared to the previous. In the input image, right? So, and that betterment that you are getting is in terms of the we can actually correlate that by its histogram as well. So if you compute the histogram of this image, we see that we are getting this histogram, which is uniformly distributed histogram up to some extent, and this is also a from a histogram. So this also basically working towards improving the contrast of the image. Here in this example, we see that we have two poor quality images, or maybe you can say this is actually good quality image, and this is the poor quality image created out of. So here you have there is a feature extraction technique called SIFT. I'm sure some of you must be aware of this. So what SIFT does is basically it takes the image and does some computations and find out, and those unique points are called the key points. And this uniqueness in the points actually is being created by analyzing the local neighborhood of the pixel and then okay. So SIFT is basically a technique which is used to extract some key points on the images, and these key points are unique in some sense. You can say that they are defining a kind of unique pattern at every every pixel. So if we are calling that this is a key point, this particular point is a key point, this particular key point, then in some way you can say that the pattern that is being created out of the intensities there is a unique pattern. So in this case, you see that when you are using the SIFT matching, SIFT based matching in the two images, we are able to only match two images, 2 points from, or 2 key points in these two images. Though both these images are same, but because this first image has poor contrast, we could actually not detect many key points there, and because of that, when we are matching with the key points from this original image, we are finding only 2 matches, right? So just to highlight that, when you are computing the SIFT key matches, you might be finding, let's say, and contrast present here, only out of images, only 2 are getting matched, right? Though this example, as the quality of this image using this algorithm, so we get a new image here. Image is same, so whatever you have here is same you are taking here, but when the contrast of this image has improved, we see that lot of matching points are being identified. So this also shows that the quality of the images increasing because of this, by use of this algorithm. Okay, this is another demonstration of the result where you have shift-based matching again. Yes.
Sir, what is the objective function? Sir, what is the objective function for this experiment, sir?
So objective function everywhere is based on that quality that we defined at the beginning. Quality of the image based on the contrast.
Sir, how can you apply, sir? Can you show me, sir, how can you apply the objective function, sir?
So I think maybe you might have joined late. So what this objective function actually does? Let me just tell you. So it considers the image.
Actually, sir, yes.
Yes, go ahead.
Sir, could you please repeat, sir, objective function? Actually, I confused, sir.
Okay. Yes, no problem. Let me just quickly go back. So this was actually objective function. QIC is defining the quality of the image, and this quality of the image is actually being dictated by the contrast. This QC is the value which gives us the contrast. So QC is actually a kind of parameter which is obtained by summing the binary values. So QC, the value of QC basically tells how many blocks you have in your image which are having good contrast, and how many blocks you have which are having the bad contrast. And before that, I just told you, we are computing with given an image, we are dividing that image into patches, and for every patch we are computing the contrast. There was
okay, QIC is the objective function, sir. Okay, sir.
The objective function, which basically tells us whenever this value is more, this basically means that the quality of the image is good, and which indirectly actually depends on the contrast. So whenever QIC is more, you can say that the contrast is good, right? Okay. So you see that in this example, the quality value is decreasing when the contrast is decreasing, or when the contrast is increasing. When the contrast is having an acceptable value, then at that time this the highest. Okay. So based on this, we are defining the objective function here. I hope this helps you in understanding. All right. So in this example, again, we are analyzing the results of this algorithm based on the number of matching key points. So here we have three cases being plotted with the help of these three colors. You see green color, red color, and the blue color. What we see in case of blue color? It says poor contrast images matching with original images, right? So this blue color actually shows the matching of this kind. Let me just clear this first. So we have two cases here. In one case where we are matching a good contrast image with the bad contrast image, and another case where we are improving the quality of the poor contrast image and then performing the matching, right? So these are the two cases we have here, and these two cases are being represented there. This first case where poor quality image is being matched with image. So here images with the original curve is going below. Having actually this is there's a problem in the drawing. This is actually about the red curve. Red curve is actually about the so let me just change this. So this is about the poor contrast. Here the score is what is happening? The original images with the images which have been improved by histogram equalization. At the beginning, I told you that histogram equalization is also a process of improving the contrast of the image. Yes, we are improving the quality of the image by using histogram equalization and then matching. So here, if you see this example, the first red curve is plotting this matching, and then this matching where the improved quality, improved image in terms of the contrast is used, but this improvement is done with the help of histogram equalization, not with the help of this algorithm. So in that case, we get this matching shown here with the help of blue curve. And then you have another curve here plotted in green color. This actually shows the matching of the original images, enhanced images where enhancement has been performed with the help of proposed technique, and you see that consistently this curve is higher compared to other two curves. What we are showing on the right on the y-axis, this actually shows the number of points that matching point that we get. So we see that when we do the improvement with the help of this proposed algorithm, then the number of matching points are consistently high for all the images. On the x-axis, we have the images, right? This image ID, like we are considering, let's say 160 images. So we have on the x-axis 160 images, and for every image, in these three different cases, how many number of matching points we are getting, that is plotted on the y-axis. So for contrast is across all the images. Okay? So that also shows that the algorithm is performing well. This is another demonstration of the result where the comparison and in terms of the PSNR also we see that the image has better quality, and this is actually when you and then ABC, the original ABC, that our proposed algorithm is performing better. And these images actually G1, G2, G3, they have been taken from this source, as I said at the beginning. So we have taken some natural images from this paper, and then we have applied the comparison based on PSNR. So this was all about the enhancement of the contrast using this proposed technique, and there can be several applications of this. Wherever you have images and you have poor contrast, you can actually make use of this technique and improve the contrast of the image. Some of the applications are listed here, like biometric applications or enhancement of the images in case of surveillance system, or in case of banking when you are dealing with the scam checks. If the checks have poor quality, poor contrast, then this can be used for improving the contrast of those images. So these are some of the applications which I have listed here, but there could be several applications. Wherever you are dealing with the poor contrast images, you can make use of this algorithm and then perform the contrast enhancement. So in conclusion, what we have discussed here. So we have discussed the contrast enhancement technique for images. This technique was based on the artificial bee colony, but we have improved the artificial bee colony algorithm by associating it on direction constraint. So there are two ways this proposed technique is actually novel. It is using ABC, but the quality parameter that we are using, or the objective function that we are using here, is our proposed function, and the introduction of this direction constants. In ABC, okay. So those two contributions are actually highlighted here: the association, the use of the direction constants, and the objective function, or the quality estimation technique that we are using to define the objective function. Okay. And as you have seen in the results, that experimental analysis says that this for improving the quality of the images of the images, and we in terms of its comparison with the histogram equalization, which is a very well tried contrast enhancement technique. Compared to that, this technique actually performs better contrast and related publication, which is on which this presentation is based on. So if you are interested in more details, I will be sharing this presentation at the, after the talk. So you can go to this link and then download this paper and then get more details about it. Okay. So these are some of the references that I have listed during the presentation. And with this, I really thank your patience. If there are any questions, I can take. I will be happy to answer.
Thank you, sir. Participants, any questions from your end? Any queries?
All right, so it seems there are no queries. I guess whoever had the queries had asked actually during the presentation. So, yeah.
Okay, sir. Thank you, sir. Thank you for your excellent talk and sharing your knowledge to us. Thank you, sir.
Yeah, thank you, madam. It was a pleasure. Thank you very much.
Thank you, sir.
So I'm disconnecting. No, madam.
Yes, sir. Yes, sir. Thank you, sir.
Oh, okay. Have a good day.
Thank you, sir. Yes, all the participants, the session is ended here. And the next session, the validatory session will be at 2:10. You all please join by that time. And the test and the complete feedback links, attendance links, everything will be given again. Okay, so all of you please reconnect by 2:10. Thank you.